We talked briefly about exponential functions last time, but we really never did anything with them. We just get you excited about them, talking about money and finance and growth and decay and all that stuff. But usually an exponential function has the format y equals something like this, 3 to the power of x. That's an exponential function. Notice your exponent's actually x. Before we used to deal with y equals x squared, y equals x cubed. Your exponent was a number. Here the exponent is x, y, x minus 2. Now if I was to graph this one, ruler just to make it nice and neat. What color? Red color. I think it's red. Okay. Let's say I want to graph that. I should use graph paper. But I'll make a table here. And I'll pick values for x and compute the y value. So this is x. And this is y. Okay, this marker is dead. Let's try 0, 1, 2, -1, -2. Let's see if that'll be enough. So when x is 0, what do we have? What is 3 to the 0?
1.
That's a 1. When x is 1, 3 to the first, 3. When x is 2, 3 squared, 9. When x is minus 1, 3 to the minus 1. Yes, that's 1/3. If you remember the law of exponents, a to the minus n is 1 over a to the n. When you have 3 to the minus 1, that's 1 over 3 to the 1, which is 1/3. Using that rule there. 3 to the minus 2. 1 over 3 squared. 3 squared is 9. That's 1/9. So when you go to graph them, you go x is 0, y is 1. X is 1, y is 3, way up there. X is 2, y is 9. Give me a ladder. We're going to need it. Way up there. X is minus 1, y is 1/3. X is minus 2, y is 1/9, and so forth. It will never hit the 0. Will never. When x is 100, what's 3 to the power of -100? It's almost 0, but it's not really a 0. So the graph looks like this. This is what 3 to the x will look like. Now if I do, instead of 3 to the x, if I do 4 to the x, or 2 to the x, what do you think the graph might look like if I do 4 to the x and 2 to the x? If I do 2 to the x, it will go through 0, 1, but will look like this, flatter than that one. It will look like this. Still goes through the 0, 1. So it rises slowly and it falls slowly. It doesn't just drop. If you did 4 to the x instead of 3 to the x, that's a steeper now one. It will look like this. That's 4 to the x. So the bigger the number, the quicker it's going to rise, the quicker it's going to drop. The smaller the number, it's going to be much slower. If I do 1 to the x, what would that be? Exactly, straight line, so it's not exponential. 1 to any power is 1. Now, if that number is negative number, then we have a problem. Because when you take a negative number and you change it to even power, odd power becomes what? Positive and negative. Doesn't look like exponential. So you're trying to get your numbers like positive numbers here. Otherwise, if they're negative, we have a problem. But notice this function is getting bigger. As you go to the right, it's getting bigger and bigger. That's called a growth problem. When you put money in the bank, your money grows exponentially. Growth problem. When you get sick, bacteria in your body grows exponentially. You hate to hear that, but when somebody sneezes at you, somebody's sick, that virus now, 1 or 2 germs will come to your body. Next thing, they multiply and you have hundreds of them. They grow exponentially. Every few minutes, that number doubles. And it's like, uh-oh, we got a problem. Sometimes we have what we call decay problem. Decay problem, they decrease instead of increase. That's a growth. So what's a decay problem looks like? If I say graph y equals 3 to the negative x, it's going to be the reverse of 3 to the x. You're going to flip it over. And it will still go through 0, 1, just like before, but now it's going to look like this. Again, if that number is 2 to the negative x, will be a little bit slower. If it's 4 to the negative x or 5 to the negative x, really steep. That could be 5 to the negative x. So the bigger the number, the quicker it's going to rise. Now, these problem again known as decay problem. But notice it goes through what? 0, 1. Sometimes we do some shifting. We go, what is the graph of y equals 3 to the x minus 2? So what is the graph of y equals 3 to the x minus 2? Well, we know what 3 to the x looks like. This is 3 to the x. We just did that. That's 0, 1. So what is 3 to the x minus 2? Isn't that shifting in the x direction by how many units? 2 units. So take this graph and shift it to the right by 2 units. So instead of 0, 1 here will be what? 2, 1. And it will have the same shape. It'll look like this. And that'll be 3 to the power of x minus 2. The 3 to the minus x, we flip that one. That's called reflection. If you remember the reflection, when you replace x with negative x, that's the reflection about the y-axis. That's why 3 to the minus x looked like this. We took this graph, we flipped it over. Reflection. Mirror image. Now, let's take an exponential function, try to find the inverse of it, because that's going to take us somewhere. Let me take, I don't know, e to the x. Y equals e to the x. Anyone doesn't know what e is? E is 2.71828 and it keeps going to the x power. So roughly 2.7 to the x power. If I graph that, if I take that function, graph it, again, that's a positive number, more than 1 raised to the power of x. is going to be exponential. This is e to the power of x. This is 0, 1. And now let's say I want to find the inverse of that. What's the inverse of it? To find the inverse graphically, we draw y equals to x. Remember that? And you're going to flip it over. And again, we'll do it together because I want you to see it. I'll take a thick marker. Let's flip that over this paper. Let's fold that paper along this dotted line and see what that picture looks like. Ready to see what the image looks like? Can you see what happened? Can you still see the x and y axis? That's the x axis, the y axis. You see it? So the inverse of that, when you graph it, the inverse looks like this. And instead of going through 0, 1, remember, this is the inverse. This point is what? 1, 0. This graph is the graph of the logarithmic function. This is really the ln of x. If I ask my calculator to graph the ln of x, that's what you're going to see. Let me go back to this calculator here. Clear. Y equals, clear, ln, what the hell is ln here? ln of x. And I asked to graph it. Oh, I got to change the window. Where's my window? There we go. Let's go from -3 to 3. I'm trying to zoom in on it. -3 to 3.
Bless you.
Look at that graph. Isn't that what we have here? It goes through 1, 0. So let's look at that picture of the inverse, the logarithmic function. This is the natural log of x. Before even I talk about the log, just looking at that picture, we know a few things about it. What is the domain? Let's look at the log function. Properties of the log. I'm sure our book will discuss that. So what's the domain? Well, not almost. Well, you got to do it like this, right? Yes. Greater than 0, all the way to infinity. So that's really rule number 1. What? It says you can't take the log. When I say the log, that includes the natural log. We'll talk about log or natural log of a negative number or 0. You can't take the log of a negative number or 0. Well, let's see. By the way, on my calculator, there are 2 buttons, if you can see them. One is log and one is ln. What's the ln, log? Log is log base what? 10, and the ln is log base e. Watch this. The natural log of negative 2 is going to say domain error. Can't be done. The log of negative 5. Can't be done. Error. Clear that. The natural log of 0. Error. Can't do that. The log of 0. Error. You can't take the log of a negative number or 0. Looking at that picture, what else do we know?
The range is negative infinity to infinity.
What is it?
Negative infinity to infinity.
The range?
Yeah.
Okay. So the range goes from negative infinity to infinity. I'll take that. But let's stay with the domain. I mean, just looking at it, when x is 1, what do you think your answer is?
0.
Yep. So that's the first one is rule number 1. I say you can't take the log of a negative number or 0. Rule number 2, the log of 1 to any base is always 0. To any base. So again, here's my calculator there. What's the natural log of 1? Should be 0. What's the log of 1? Should be 0. Unfortunately, my calculator does not give me log base 3, log base 4. Some of you might have a calculator that does that. Maybe my fancy one. The one I don't use. Just sits here. One day I'll learn it. Maybe this one has it. Beautiful, colorful one. And I couldn't even tell you where the log, oh, I see it. There's the log. Once it charges, come on. Here it comes. Okay. Where's calculator? Here we go, enter. And let me take the log. I just saw that. Oh, look at this. You can put any base there. So let's put base 3. Base can't be negative. Let me move the mouse up there. Ah.
You can just hit the right button.
I have a mouse here actually, but
The right arrow.
let me do the log of 1. We said the answer to any base should be what?
0.
0. Enter. Is 0. Doesn't matter what the base is. Log base 27 of 1 should be 0. Now if I use a negative base, where's negative here? Negative 3,
An error.
yep, of any number, the base can't be negative. It gives you a whole story.
Just like giving it.
You can write an essay about it. And it says, no, you can't. So the base has to be positive. So anytime you want to do the log of base to any number, make sure first the base is positive and the number itself that you write there is at least more than 0. Because if it's less than 0, can't be done. If it's 0, can't be done. And if the answer is 1, then the result is 0. So that's rule number 2. We have 2 rules about the log. We're going to list about 5, 6 rules now. Second, clear. Delete. Shut down. Where'd you go? Oh, here we go. It is a nice calculator, just slick one, everything, but Rule number 3. If I come in and I said to you, you know what, I know I didn't discuss the log, but can you tell me, this is the next rule, or let's make that y. Let me call that y instead of x. This is y equals x. Now, if you're given two things, we should be able to solve for the third one here. When I say two things, either b, y, and x. If you're given two of the three, we should be able to solve it. Well, rule number 3 says, if you look at your calculator, the log and 10 to the power, because the base was 10, on top of each other, means they are the inverse of each other. You can take this and change it. You can go back and forth and write that b to the x equals y. That's rule number 3. If you want to have a nice clean sheet of paper, write these properties on them, go ahead, because as we go through the stuff, if you're not familiar with them, you want to refer to that sheet of paper. I'm going to be putting notes in between them, so it makes it tough to see which one's which. So if I come into you and I said, can you tell me what the answer to this? You go, I don't know. I don't have a calculator that does base 3. Can I borrow your calculator? I said, no. That's mine. Can't touch it. But if you change this to exponential, I should be able to write that, what? The base, which is 3, to x equals 9. 3 to what power is 9? X will have to be 2. So the question really, 3 to what power is going to equal to 9? The answer is 2. If I write this problem, log base 2 of y equals 5. Can you tell me what y is? Again, if you're given 2, we should be able to find the third one. If I change it to exponential, that says what? The base, which is 2, to the answer should equal the number, which is y. 2 to the 5th, y equals 32. Log 27 base b equals 3.
9.
Try again.
No, it's not. It's not the cube root of 27.
Think about it.
3.
3?
Oh, yeah, you're right.
Yep.
Yeah.
Because you have to write that what? The base cubed has to be 27. Now, what number, if you cube it, the answer is 27? Notice 27, if you take 27, isn't that 3 cubed? So the base will have to be 3. So we really can't find, we can find the base, the log of any number to any base, except when I give you some crazy numbers. And sometimes we tend to have fun with these problems. I go, well, solve for x. Or a here. Solve for a. I don't need a calculator for that to help me with it. I should be able to do it without a calculator. Change it to exponential. If you change it to exponential, what are you going to have? 2a minus 3 equals what? 4 to the power of 2. The base raised to the answer. Doesn't matter which side you put them on. 2a minus 3 equals what's 4 squared? 16. 2a equals what? 19. A equals 19 over 2, which is 8.5.
9.9.
Or 9.5, yep, thank you. So, by the way, if they said give me the exact answer, if you put 9.5, that would be correct. Because you're not rounding here. Where if you did 4 over 3, you know 4 over 3 is what? 1.33333, goes on to infinity. So if you go 1.3, that becomes an approximation. That's why they mark it wrong. But since this is exactly the answer to this, that's it. You can divide them. That would be a correct answer. This would be the correct answer. Either one. So now we know rule number 3. Let's look at rule number 4. I'm trying to go through the rules here. Now, before I list that rule, if you were to multiply x to the power of m times x to the power of n, what would you do?
Add x to the n minus n.
Try again.
Are you multiplying?
Yep,
You add them.
you add them.
And then dividing minus.
I'll give you a way to remind me. You're making me mad. So he's making me mad. Actually, I'm more than mad. I'm multiple mad. Mads, with an S, plural. When you multiply, what do you do? Add. When you divide, subtract.
Oh.
So when you multiply, you add. When you divide, you subtract. So now, when we're looking at the log, if you have a multiplications, when you have multiplication, you can actually break it down to what? Addition. And an example, what is the log base 2 of 8x? If we give you that promise, can you simplify that? Yep, the log of 8 base 2 plus the log of x base 2. And can you find the log of 8 base 2? Yep. 2 to what power is equal to 8? So here the answer is 3. 3 plus the log of 2 base x. Sometimes you have big numbers. Log of 75 base 5. Now to simplify that, please. Yeah, good luck. Because if you go, I'm going to call that x, then to change it to exponential, 5 to what power is equal to 75? Your guess is as good as mine. 5 squared is what? 25. 5 cubed is what? 125. So somewhere between 2 and 3. Well, I don't want that. I don't want somewhere between 2 and 3. I want you to simplify that. Well, I can take the 75 and rewrite that as what? 25 times 3. Isn't that 75? And I should be able to rewrite that as log of 25 base 5 plus log of 3 base 5. 5 to what power is equal to 25? 2. So the answer to this is 2. I'm going back to maths here. When you multiply, you add exponents. When you divide, what do? Subtract. Let's do division here. If I have x to the m over x to the n, you subtract that. You keep the base and subtract that. So that's rule number 5 now. If you have log x over y base b, you can actually rewrite that log base b of x minus log base b of y. Here's an example. What is log base 2 of 0.125? .125. Isn't that 125 over what? 1,000? And if you simplify that, that's what? About 1/8. But if you go through it, 125 over 1,000 is 1/8. You can divide by 5 and keep simplifying. So now I can apply rule number 5. And I go, that answer is what? Log base 2 of 1 minus log base 2 of 8. What is log 1? 0. Rule number 2. And this is what? That's 3. 2 to what power is 8? 2 to the power of 3. So your answer is -3. And if we write, if I take 2 to the -3, should give me 0.125. Here we go. 2 to the power of, where's power? Where'd you go? Of -3. If we are correct, we should see 0.125. Right there. We have one more property of the log. I'll make the other one maybe I'll make it 2 instead of 1. Rule number 6. If you have power to power, that's power to power. What can we do with it?
N times the log of.
Yes, n times the log of a base b. You can take that power and move it to the front. And that's all the properties of the log. Now, if I have this problem, log 25 base, to the power of 7 base 5. I really don't want to write 25 to the power of 7. I don't want to do the math for that because that's a big number. 25 to the power of 7. Yeah, good luck me finding the answer to that. And trying to find the log of that number to base 5. I'd rather stick toothpicks in my eye than do that one. So what can I do? I can take the 7 and move it to the front. That would be 7 times the log of 25 base 5. 5 to what power is 25? 2.
Oh, right.
Yep.
Yeah.
That'll be 7 times, the answer to this is 2. What's the answer? 14. So if I take 5 to the 14, I should get that stupid number that you see there. Let's see if that's correct. 5 to the power 14. And if we did it right, we should match that number there. Right there. Same exact number. Where this comes in handy here, if you have e to the power 5, what's the answer? Try again. It's 5. I'll give you this. You got the 5 right.
All right.
But you got log e base e.
Now 1.
That's a 1.
That's a 5.
This e to what power will equal to e? 1. So the answer to this is a 1. Log e to the negative 3 base e. Negative 3 times, if you want to do it the long way, log e base e, and that's a 1. 1 times a negative 3, that's a negative 3. Log base 10 of 10 to the 4th. Are you sure? I got a 4. Here's what we're noticing, or at least I'm noticing that. I don't know if you spotted. If these numbers are matching, your answer is always what?
100.
The exponent, the final answer. The final answer. See it? Yep. Log 7, base 7 of 7 to the power of 21. What's the answer? 21. Where's that going to help me? Solving exponential functions. Let's see what I mean by exponential functions. Because the topic is really here, solving logarithmic and exponential functions and properties of logs. Let's say we have this problem, 3 to the power of 5x minus 2 equals 27. And I want to solve that. It might look ugly first, but if you look at it, this is 3 to what power? 5x minus 2. Can I take the 27 and write that as 3 raised to a power? 3 to the third. And if this side is equal to that side and the bases are the same, the only way that could happen if what? If the exponents are the same. So this exponent has to equal to that. Now can I solve this? 5x equals what? 5x equals 1. You divide both sides by 5.
So this is only possible if the 3's are the same, right?
If you can write this as that number raised to a power. If not, we gotta look for something else. 2 to the power of 4 minus 3x equals 32. The 32 is 2 to what power? That's 2 to the 5th.
So theoretically, you could still do it if it was decimal, right?
Well, we'll see. I'll give you on the next example. We'll see if you can do it.
Oh boy.
So 4 minus 3x equals what? 5. Now to solve it for x, I got to move the 4 to this side. That becomes a negative 4. What's 5 minus 4? 1. And if you're going to solve it for x, you got to divide both sides by what? By negative 3. Divide, not subtract. So x equals negative 1/3. Again, we can do that as long as I can take that number, make it 2 to the 5th. The question just came up. What happens if I can't make that number? What about if this is a decimal number or just a different number? So I'll start with one that's not even decimal. I have 10 to the power of 5x minus 3 equals 4. Now there is nowhere on earth I can take the 4 and write that 10 to a power. I have no idea. So how am I going to solve that? Now that's an exponential function or equation. Not a function, that's an equation. When you have an equation, whatever you do to one side, you got to do the same thing to the other side. Right? This number is 10, right? Let's take the common log of both sides. Again, I didn't put a base. If there is no base, it's assumed to be what? Bless you. Base 10, that's known as the common log. So I just want to put it now, but usually you won't see me write the 10 there. Now, why did I choose 10, not the natural log, not log base 3? There's a reason why I picked the log base 10. Yes, look at these. They're the same thing. And if these are the same, we just finished saying that, rule number 6, your answer is going to be what? Whatever the power is. Right? If these guys are matching, your answer is going to be the power. So your answer to the left side is going to be what? 5x minus 3, the log of 4. Now to solve it for x, what do? We move that minus 3 to this side. When you take it to this side, becomes what? Positive 3. I like to put the 3 in the front, not in the back. Because if you put 4 plus 3, people might have a, well, 4 plus 3, let me add that, make that a 7. Can't. This 4 goes with the log, the 3 doesn't. And if you want to solve for x, what do? Divide by 5. So if they ask you for an exact answer on the homework, that's what you have to write. This one. Don't try to go to the calculator. If they said write the answer to nearest hundredth or 2 decimal places, then go ahead and use the calculator. So if you go to the calculator now, this is 0.72. Notice there's more numbers. So this is exact here. If they say give me the exact answer, This is an approximation. So if they ask you for the exact and you give them this, definitely they'll mark it wrong. Just like if they ask you to round the answer to 2 decimal places and you go and give them this, they will mark it wrong too, because they either want it this way or that way. Now, I made a statement last class. I said if you can get 10% return on your money will double every 7 years. Remember that example that we put $5,000 for me, and by age 84 I had like $10 million? Well, let's see. Can we prove that at 10% return your money will double? Because the statement I made, 10% return on your investment. The claim I made, your money will double every what? Every 7 years. And I said to you last time, it's really not 7, it's 6.93 years even. So we're going to do the math and prove that. So I'm going to go to the bank tomorrow, and I'm going to deposit $1 with them. So my initial deposit is 1. Remember we said the banks today use the amount of money you will have is the present value e to the RT. That's what they use to calculate how much money you have. This is only if you make in one deposit, one time, not every month. That's a different story. That's called annuity. The equation for that completely different. This is a one-time deposit. You put in $1 there, your money should double. Let's see how long will it take it to double at 10% return. So if you go and put $1 in, that means your money is going to be worth, when you go to cash it, how much? 2. It's going to double that number. E to the power, the rate is 0.10 times t. And I want to solve it for t. A is the amount of money. P is the present value, what you're putting today.
Okay.
So A is the amount. How much money will you have? 10 years. P is the current value, current deposit. When you go to the bank, the present value, if you want to call it the present value. R is the rate, the interest rate, and T is the number of years. So how would I solve that equation? Take the natural log. Why the natural log? Because I got E here. So I'll take the natural log of both sides. Now a lot of people get confused as why are you canceling the natural log in E? Because if you think about the natural log is log base what? Log base E. That's what the natural log is. And notice these numbers are matching. If these numbers are matching, your answer is always the power or the exponent. So what's the answer? 0.10t. And what's t equal to? ln of 2 over 0.10. We couldn't do the math last time because we didn't cover the log.
So you can just go from natural log of E to log base E to E?
Well, that's what the natural log means log base E. So we just don't write log base E, we call it natural log. So when you see ln, that's log base E. Just like when you see the log on your calculator there, that's log base 10. So let's do the math and see what that number is. What's the natural log of 2 divided by 0.10? And what do you know? 6.93 years. 931471806. your money will double every 6.93 years roughly. Less than 7 years. And that's why if you put in, somebody left you 5,000, we're not going to go that many years, but today, somebody just gave you 5,000 bucks, put them in an account for you, says you can't touch it till you retire. Now most of you are under 20 years, 20 probably. Let's say you're 20. And they say you can't touch the money till age 62. So how long the money is going to sit in that account if you're 20 years old today?
42 years.
So for 42 years from today, at 10% interest, let's see what that 5,000 will be worth. E to the power of r, which is 0.10, times t, which is 42. And let's see how much money you will have. 5,000 times e to the power, where's my e? E to the power of 4.2. In 42 years, at age 62, you will have $333,431.66 when you go to close that account at age 62. You say, I want to cash that. I want to go to North Carolina, South Carolina, Florida, buy a nice house there and retire. Play golf every day. Not me, I'll be dead. That golf drives me nuts. I get so mad, I want to break all the clubs and throw them in the water and go home every time I play. So I know that will kill me. I'll be so mad. Ah! You can put a cup of water on that golf course. I can drop that ball in that cup of water. I just see water and that ball is going to that cup of water. I'm telling you, you can put this cup right anywhere on that course. And I could be anywhere. That ball is going to go in. Like,
Gotta put some water in the hole. Get it in every time.
Yeah, that's true. So that's why we're looking at a log, so we can solve exponential equation. If you're into forensic science, when they find a dead person, a body there, and they want to estimate how long the person is dead, well, they use these equations. Radioactive. Sometimes you hear there's radioactive material out there. And they say, well, somebody dumped all this stuff here. Now, this armory here, it was known for making guns. We used to make guns years ago here for the war. And if you've never been to the museum, go to the museum. It's beautiful, actually. You see all these guns split in half from being used in the war from the heat. Really, it's actually cool to walk through it. I've been through it a couple of times. Well, in Ludlow, I think, or Indian Orchard, they were actually working on nuclear weapons at that time. And some people work on some nuclear waste without knowing that's nuclear actually material there. They had all these people work on them, and they all have these diseases now that you see them walking. Some people have these bumps on their arms and legs and everything. You see articles about them all the time. They're all coming up with something called the crust disease, which is hardening of the artery, and that's from being exposed to radioactive material. But what we know about some of the radioactive material, that the lifetime of them, it might be 3,000 years. And what does that mean? I can actually get the information on uranium and see what half-life of uranium is. Let's see. Where's my phone? I can do it on my phone. Oh, it's easier probably. Oh. What is the half-life of uranium?
The half-life of uranium is about 4.47 billion years.
4.7 billion years. So this is half-life of uranium. 4.7 billion. That's 10 to what power? To the 9 billion. Million is 10 to the 6. So basically, move the decimal point 9 places to the right. That's the half-life of uranium. Meaning what? That's half-life. If we take a bucket, 5-gallon bucket, and we bury it in the ground, in, let's say the 5-pound bucket there, in that number, 4,700,000,000 or 4,700,000,000 years, we down to 2.5. You shrink half that amount. So that material will stay in the ground for not billions, trillions and gazillions of years there. I don't think it's anything's gazillion there. Google year. When we find bone out there, you go, well, we believe this actually bone belonged to a dinosaur that roamed the earth that many billion years ago. Well, how do they know? We measure carbon. The amount of carbon decreases. We can get the half-life of carbon. That might be a more reasonable number. What is half-life of carbon?
Carbon is stable.
Is it carbon 14, I think?
It's 5,715 years.
5,672 years.
Let me think about that. Okay, I found this on the web for
5,600.
5,600.
5,715 years. That's carbon 14. So what does that mean? We find a leg of a dinosaur, femur. We take it.
You know it has carbon in it.
Yep.
It's carbon-based.
We can measure how much carbon left in it. Percentage. We know what average, like when you're alive, we know what percent of carbon there. We have that amount of carbon, you're 100% carbon. Now when you die, start to shrink, less. We can use that equation. We said, okay, we believe this one has still 0.25% of the carbon that was in it. And based on that, if it has 0.25 today, we can tell you actually how many years. Why? Half-life. This is the half-life of carbon. We can calculate the rate of decay of carbon, which means what? At 50%, that's what half-life is, 0.5 or 50% is equal to 100% e to the power of negative, when it's decay, negative r times t. I'll do it this way. That's what 50% means. Half-life, you can have 50% of that. So 0.5, if you change it to a decimal, 100% is actually 1 as a decimal number. Negative r times t, which is 5,715 years. We can get the rate of decay now. We can get what r is for carbon 14. We take the natural log of both sides. And these two will cancel each other out. You end up with the power. Can we calculate what r is? We divide both sides by negative 5,715. So the rate of decay for carbon 14 is the natural log of 0.5 divided by negative 5,715. The rate is 0.0001213. I'll stop here. There's more numbers. So now the equation that describes carbon, carbon 14, will be the amount of carbon, that's the amount, is initially what was the present value, which is 100%. Let's do 1 here, which is always 100% before you die. E to the power of negative r, which is 0.0001213 times t. So we find this piece of bone there. We measure the carbon in it. We find out it has what? We said 0.25, 25% left. So you put 0.25 here. We take the natural log of both sides. The natural log and e, they'll cancel each other out. And I can solve for t now, which is we believe this dinosaur been missing for 11,000 or dead for 11,430 years ago, based on the amount of carbon that we found in it. We found out actually that people lived on Earth way before us. They knew about fire. So how do they know that? Well, they found out of burned wood actually. A piece of wood that was burnt like about 11,000 years ago or 800 years ago. They go, oh, they knew about fire at that time. It was a cabin actually they found that was burnt. He said, let's measure the carbon in that, and based on that, we can figure out when did that actually cabin burn, based on the amount what's left there. So that's how we solve exponential equation. The last piece here, how do we solve logarithmic equation? Sometimes you have an equation that has log in it, not exponential. And that's where we're almost done with this one. I know it's a long video and a long lecture. I'm getting tired too. I'm getting hungry too. Let's see. Let me take an equation. Now I have no idea what the answer is going to be. I'm just making things up. And sometimes I go, oh God, I wish I thought about this more. Because I start making things up and it doesn't work out the way I planned it. So I'm making an equation there and I want to solve it for x. That's a logarithmic equation. How would I solve that? The first thing I notice on the left side, I have a log minus log. Maybe I can combine them together using one of the rules we listed. I think rule number 5. That used to be division. So the left side used to be notice since the bases are the same, this side is equal to this. It says equal to that. The sides are equal. You have the log on both sides. The bases are the same. Bases are 10 here. The only way these two will equal to each other if what? If this one is equal to this. That's the only way. Can we solve it now? You multiply both sides by x. You got to take that x and bring it to this side. 3 equals what? What's 7x minus x? 6x. X will have to be what? 0.5 or a half. Now, when you see equations like this, you got to do one more thing. You got to look at it, make sure when x is 0.5, if you plug it in, that expression is not a negative number. Because if that's a negative number, can you take the log of a negative number? You got to throw that answer away. In this case, when x is 0.5, 3 plus 0.5, that's a positive number. I'm okay. That's a positive number. I'm probably going to be okay. But if one of them is negative, you definitely, like, if this was x minus 3 here instead of a plus, and that's your answer, you go, what's 0.5 minus 3? Negative number. You can't take the log of a negative number. I can't use it.
So what would you do?
If that's the only answer, then it has no solution. You could have a problem that doesn't have a solution to it. Well, I lucked out here because both sides have the log in them. Well, let's try another one that doesn't have a log. Bless you. And let me think about this. Maybe I'll try to make it work out. Now I made this, I try to do it in my head, so hopefully it's going to work out. That's a minus here. X minus 3. Is it hot here?
Yeah.
Yep, I'm dying too. It's like, oh.
It's like 10 degrees cooler than normal.
Too bad we can't open the windows outside, suck the air in. What can we do here?
Multiply the...
Okay, that's an addition, so there used to be a multiplication. I'll take that.
You could switch the 1.
What do you mean by switch the 1?
Just try to plug the x.
So we can switch the 1. I'm trying to figure out which direction. Where is he going with it?
So you only multiply those two.
Oh yeah, you could do it.
Yep. After, yep.
Switch the 1 to a log 10 base 10.
Oh, I like that. I see where he's going now with it. First, let me multiply this. Let me clean it first. But I like where you're going with it. That's x squared minus 3x. He said, wait a minute. I can use rule number 3 here. What's my base here? 10. Let's go from log to exponential. I should be able to write this as what? X squared minus 3x equals the base, which is 10 to what power? 1. Rule number 3. The base raised to the answer is equal to that expression. What's 10 to the power of 1? 10. Now we have a quadratic equation. Factor that. I try to do it like where it factors nicely. And we have two solutions. X will have to be what? 5 or x equals negative 2. Remember what I said. Plug your answer. When x is 5, this is positive. I'm okay. This is positive. It looks like I'm going to be okay. When x is negative 2, can you take the log of a negative 2? So you can't use that answer. So you only have one solution to that problem. X equals to 5. And if you really want to prove it, go through it completely and check it out to see if it works. Go, let's test it. Log of 5 plus log, what's 5 minus 3? 2. This is addition. It used to be what? Multiplications. 5 times 2, which is 10. Remember, the power here is 1. Since these numbers are the same, the answer is 1, whatever the exponent is, and it is equal to. But the least you want to do is what I did here. See if these numbers, the negative numbers, any number actually, not just the negative. Because if this was a plus 2 here, what's 2 minus 3? That'll make that a negative and you can't use it. So I don't want you to think just because it's a negative number I can't use it. Sometimes it could be a positive number and you still can't use it.
Sometimes it could be a negative number and you can.
Yep, absolutely. You could have a negative number if this was x plus 3. I didn't have this. Or this is x plus 3 and this is x plus 5. The minus 2 will be fine. The last thing I want to talk about, and I'll stop the video and see if you have any questions. Give you color problems to try. Again, you don't have a fancy calculator like mine. Let's say you don't have that. And I ask you, what's log 7 base 3? What is that equal to? And I want to know the answer to that. It's not like, well, I think it's this. Well, 3 to the power of 1 is 3, so it's more than 1. 3 squared is 9. Oh, 9 is bigger than 7. So somewhere between 1 and 2. Closer to 2 than 1. But I want to find the answer to that. I want the answer to 4 digits, 4 decimal places. Notice if I change that to exponential, it will say what? 3 to the power of x equals 7. Now, I'm going to break the room into 2 groups. This side of the room, let's take the natural log of both sides and solve it for x. Not the right side of the room. The right side of the room, I want you to take the common log. And let's solve it and tell me what is the answer to 3 decimal places. Notice how we have exponents there. See that 3 to the x? Rule number 6 is when you have exponent, what can you do? Bring it to the front. Doesn't matter which side of the room you're on. Applies to both of you. So this will be x times the natural log of 3 equals the natural log of 7, the left side of the room. The right side of the room is going to be what? X times the log of 3 equals the log of 7. That's a multiplication. To solve for x, we're going to divide both sides by what? Natural log of 3 here on the left side of the room. The right side of the room, we're going to divide both sides by what? The log of 3. I made you do it 2 different ways, broke the room into 2 groups, because I want to show you if I do the natural log of 7 over the natural log of 3. Here's my calculator. Can you see it? Let me try the ln of 7, close the parentheses, divided by the ln of 3. There's one answer. Now let me try the log. People did it with the log. The log of 7 divided by the log of 3. And look at that answer. Is it the same answer? That's called the change of base rule. So now you can find the log of any number to any base. The log, you don't have to go through this math like this. If someone asks you, we'll make that a rule, the log of a base b, you can make it the log of a, that's the common log, over the log of b, or the natural log of a over the natural log of b. So if I said, what's log 52 base 17? You have an option. You can do the common log of 52 over the common log of 17, or the natural log of 52 over the natural log of 17. Either way.
That's log B on top, right, not 10B?
Yeah.
Log, yes.
This is another rule.
That's actually called the change of base rule, you know. But it is a rule. It says, like, if you want to find the log, you see your calculator has log base 10 and log base e, that's it. So if you see a problem log base 3 and 7, 9, 15, and you go, oh, I'm in trouble. Not really, because you can use the change of base here. So natural log of 52 divided by the natural log of 17. And the answer to that is 1.3946. 15667.